Hi again, my name is Brechtje van Wezenbeek and I work for Deltares and the Delft University of Technology. In the previous video, I introduced basic ecological concepts. In this video, I will extend on this and I will tell you about the importance of biodiversity and succession and take a peek at how to use these concepts for design. Let's start with biodiversity, as biodiversity is one of the fundamentals of ecology and of life. Biodiversity is in the food on your plate, in the medicines that cure you and in the clothes that you wear. Biodiversity refers to ecological diversity on different scales. But if you hear ecologists talk about biodiversity, they often refer to species diversity, which is the number of species in an area or in an ecosystem. Species diversity is an essential element of ecosystem functioning. It enhances productivity of ecosystems and increases stability of ecosystems. This can be illustrated by a simple example. Imagine we have a grassland with two species, a blue and a green species. The blue species is more productive when it's colder, and the green species is more productive when it's warmer. If you only have a single species, your grassland will lose productivity under changes of temperature. This way, a grassland with two species with different traits is more stable with respect to productivity and is more robust to temperature changes. Additionally, productivity of the mixed species grassland may even be higher in each year, as species may not completely overlap with respect to growing seasons, allowing for them to partly replace each other within a year. So biodiversity is considered to increase the productivity and stability of ecosystems. In addition, biodiversity is also considered to increase the resilience of ecosystems. This means reducing the vulnerability of ecosystems to disturbances. It is easy to understand that a forest with only a single type of tree species is very vulnerable to diseases or to storms, actually to any kind of disturbance. So ecological resilience is the capacity of an ecosystem to deal with disturbances and still be able to bounce back to the original healthy ecosystem state. Ecological resilience is envisioned as a ball in a valley, and with each disturbance the ball is pushed out of the equilibrium, but will roll back to its original position. I have talked about productivity, stability and resilience, but you have probably already figured out that ecosystems are never really stable. They are not engineering structures that are solid and stay in place. Dynamics form an intrinsic part of ecosystems. Ecosystems evolve through succession. Succession refers to the sequence of, mostly plant species, that succeed each other as the ecosystem matures. The basic assumption is that external conditions stay more or less the same. Ecological succession is started by pioneer species. These are species that are the first to colonize. They are generally species that are specialized and that can survive harsh conditions. For example, English cordgrass, mentioned in my previous video, can colonize intertidal flats when no other plant species is able to. That is because it's salt tolerant and can withstand being submerged. Other pioneer species are sandcows grass. Maybe you have seen this on the beach, where it sets off dune formation. Pioneer species are often annual species. They ameliorate the environment so that other species that are secondary in succession can start establishing too. These secondary succession species are often perennial plants, such as herbs and small woody plants. They are followed by shrubs, and the final stage often contains trees. The final stage of succession is generally called the climax stage. Sometimes succession zonation stages can be visible in an ecosystem as different zones. For example, looking at a salt marsh, the marsh zones from the intertidal flat towards the land clearly reflect different succession stages. The zone closest to the intertidal flat is called the pioneer zone and is inhabited by pioneer species such as English cordgrass or in Latin Spartina anglica, and glasswort in Latin that is a species of Salicornia. You can find it in your supermarket, and a personal recommendation, it goes well with fish. Then the lower marsh zone is inhabited by secondary pioneer species, and you see that in the middle marsh the shrubs come in. This is a really diverse zone with a lot of different species and beautiful flowers. The high marsh can be dominated by grass species that form a rather homogeneous vegetation cover. This zone is only submerged a couple of times a year by really high tides. However, in the end, a high marsh will naturally develop into land with herbaceous forests on it. This is actually a different ecosystem, as it's no longer occasionally submerged under seawater, so no longer called a salt marsh. What types of ecosystems are actually relevant for building with nature designs? If we talk about flood risk reduction as the main function, we automatically focus on systems that occur on the boundaries between land and water. The type of ecosystem that occurs there depends on the abiotic conditions. These conditions set the boundary conditions for ecosystem development on different scales. If we look at a very large scale, the first variable that determines ecosystem development is temperature. For example, most mangrove species do not tolerate below zero temperatures, and reef-building corals can't tolerate water temperatures below 18 degrees Celsius. Temperature is also reflected by latitude, and here the climatic zones, Arctic, temperate and tropical, can be distinguished. If we zoom in to a more detailed scale, the main determinant of ecosystem type is whether we are in fresh or in salt water, as many species do not tolerate high salinity levels for long periods of time. Then, the most important factor is whether the system is sheltered and dominated by fine sediments or exposed and dominated by sandy sediments. In temperate zones along sheltered coasts, marshes can establish. Along sandy coasts that are characterized by high wave impact and low nutrient availability, marsh grasses cannot grow. Here we find our sandy beach and dune systems with their own characteristic species assemblages. Finally, within these systems, submergence time is crucial. Where regular submergence under salt water is a stress for plant species, it is a requirement for oysters, mussels and corals. These different factors, temperature, salinity, exposure and submergence time, determine the type of ecosystem that will develop. This means that you cannot create any ecosystem wherever you want it, simply because you cannot control all these factors. In the same way, you cannot control how effective an ecosystem is in performing your design function. But we do know that coral reefs are really effective in breaking waves. Seagrass beds, on the other hand, are generally subtidal and more effective for protecting sediment against erosion. So, the effectiveness depends on ecosystem and species characteristics, like the height and the biomass of vegetation. So now back to the design. Wave attenuation and erosion protection are functions of ecosystems that you can use in your designs. Let's build a house together and think of the house as my ecosystem. Again, you cannot build an igloo in the desert, of course. So the type of ecosystem that you conserve or restore is limited by environmental conditions in place. The materials we use, like bricks and wood, are the living species. With respect to these species, you should pay attention to the pioneer species that are able to initiate the succession cascade. Some of these pioneer species may also be described as foundation species. They form the foundation or the basis that the system is built on. For example, oysters construct an oyster reef, and in and on the oyster reef a whole assemblage of other species will live. So pay attention to the first colonizers. Then you should be specifically aware of what are called the keystone species. The keystone species are always pretty crucial for ecosystem functioning. The term originates from architecture, where for big arches there's a single stone in the middle that holds together the entire arch construction. If you remove this stone, the arch collapses. Similarly, for keystone species, if they are removed from an ecosystem, for example, due to diseases or to overfishing, the ecosystem collapses. Often those species fulfill a crucial role in the food web, and they are mostly not the top predators, but they are, for example, a herbivore. A good example of a keystone species are urchins on coral reefs. Algae also live on coral reefs. They can overgrow and smother the coral. Fortunately, urchins graze on these algae, keeping the coral clean and healthy. But you can see the problem. If we overfish the urchins, algae become dominant on the reef, smothering the corals and killing them. Then, last but not least, please pay attention to the size of the ecosystem. Not only from a hydraulic perspective, so how extensive does it have to be to achieve a certain amount of wave attenuation, but also from an ecological point of view. Larger ecosystems are inhabited by more species and so are more diverse and more stable. So I have talked about biodiversity, productivity, stability and resilience, properties of ecosystems. You now know that ecosystems are dynamic, evolving through succession, and that the types of ecosystems relevant for hydraulic engineers generally lie at the margins between water and land. When designing in these environments, two things are crucial. First, to know the abiotic conditions, and second, to understand their implications for ecosystems. Thank you for your time and attention.